So as I mentioned in the previous video 4.7, all redox reactions contain equal and opposite reduction and oxidation reactions. In other words, if something is being oxidized or losing electrons, those electrons have to get stuck onto something else has to get reduced. And so we can think about a full electrochemical or full redox reaction as something that contains both reduction and oxidation reactions. We can actually parse that or break that full balanced chemical reaction into what we call two half reactions. Half reactions are really just the oxidation step and the reduction step. And so when we're balancing redox reactions, it's a little trickier because we need to take into consideration both of these steps. And so it's a lot easier if we actually just break the full electrochemical reaction, or the full redox reaction, into its two half steps, into just the oxidation step and the reduction step, balance those, and then recombine them to get the full balanced chemical reaction. So let's do this with an example. So let's do this with the dichromate ion in acidic NaCl solution. So the dichromate ion is this one, chromium, two of those bound to 7 oxygens, and it's got a 2 minus, and so we're going to say that's aqueous, plus chloride, aqueous, makes chromium 3 plus, aqueous, plus chlorine gas, aqueous as well. And so where we're starting here is a totally unbalanced reaction. This reaction is occurring, and we can actually start to look at this and notice that, well, chromium is probably in a different oxidation state here than it is in here, and chlorine is in a different oxidation state there than it is here. We also can notice that there's some oxygen over here, but there's no oxygen over here. So this is sort of this unbalanced state that's just showing my oxidation and reduction steps. So let's break these out into their respective steps. So let's first write out the oxidation step, and that's going to require us to assign what's being oxidized and what's being reduced. So let's look at chromium in this case and oxygen, and let's assign some redox or some oxidation states here. So if oxygen is typically 2 minus, then there would be minus 14 on this side alone, which would mean if this whole thing is minus 2, then the chromium would need to be plus 6, right? Because that would be plus 12, 14, minus 2. So each chromium atom or ion here is going to be plus 6, and each oxygen is minus 2. Chloride in this case is going to have the oxidation state the same as its ion charge, which is minus 1. Chromium over here is 3 plus. We can already see we're going from 6 plus to 3 plus. And then chlorine, remember, is that group 7A. It's that halogen that binds to itself. That's the elemental form of it. And so it's got an oxidation state of 0. Okay, so let's think about oxidation here. Chromium is going from 6 to 3 plus. So that's actually a reduction reaction. That's gain of electrons. But chlorine is going from minus 1 to 0. That's actually loss of 1 electron. So that's what's going to be our oxidation reaction. So we can write this up as chloride aqueous. That is going to proceed to make chlorine aqueous. It's clearly not balanced, but all we're doing is writing out the respective half reactions here. So let's write out the reduction reaction then, which we just already identified. That's going to be the chromate ion, Cr2O7 2 minus. That gets reduced to chromium 3 plus, both of these aqueous. Okay, so that's the first step. So step 1 in balancing redox is write out and identify the half reactions as we've done here. So that means really step 0, the step before this, would be assign oxidation states. That's always going to be the first step. So assign oxidation states to everything, then identify what's being oxidized, reduced, and write out their respective half reactions. So just the oxidation step and just the reduction step. That's where we'll start. Okay, so step 2 here is to balance each of these individual half reactions for the elements that are present, except for hydrogen and oxygen. We're going to do those in a separate step. So let's take our first oxidation step, so chloride to chlorine, and we can pretty simply see that all we need to do is add a 2 there. So 2 chlorides, those are going to proceed to make 1 chlorine molecule like that. Everything's balanced in that step. So that's our oxidation step. And our reduction step, then we just need to balance only the chromiums because we're negating hydrogen and oxygen. We've got 2 chromiums on the left side, only 1 on the right. So this is going to be the chromate ion 2 plus or 2 minus proceeds to make 2 chromium 3 plus ions. Okay, so the third step here is to balance the remaining hydrogen and oxygen in each of these individual half reactions. So let's do this in 2 different steps. So we'll first use water to balance the oxygen. So we'll add water to the opposite side of the half reaction if there's oxygen to be balanced. And then we'll add H plus or protons to the opposite side to balance out whatever H's came from the addition of water. So the first step here in the oxidation step is straightforward because it's really already balanced. There's no hydrogen and oxygen. We don't have to worry about it. So I'm just going to rewrite 2 chloride to chlorine. The reduction step, though, has some oxygen in it, so that's where we need to be careful. So we'll start with just writing out the chromate ion, and then I'm going to leave some space here. And then we have the 2 chromium 3 plus on this side. And so the first step here is to use H2O to balance the oxygen. So we've got 7 oxygens on the left side, which means that we need to add 7 waters to the right side. 7 waters make 7 oxygens on the right and 7 on the left. So those 2 are balanced. This will be a liquid. And then the second step is to use H plus to balance H on the opposing side. So we just added a bunch of H now. So this side's got 14 hydrogens. So we would need to add 14 hydrogens to this side. So if you count everything up, we've got 2 chromiums on both sides, we've got 7 oxygens on both sides, and we've got 14 H pluses on both sides. So that is the second or the third step in the balancing. Okay, so step 4 then is to count the charge on both sides of each half reaction and make sure the charges are balanced. We need to have the same amounts of charge on both sides, and we're going to use electrons to balance out charge where we need to. So I'll write down here 2 chlorides makes Cl2. So let's look at the charges on both sides of this half reaction. So if I look to the left, I've got 2 minus 1 chloride ions, and on the right I have only these oxidation states of 0 or no ions at all. So I've got 2 minus on the left and 0 on the right. So that means I need to tack on 2 electrons to the right side, and now I have 2 minus on the left, 2 minus on the right. Okay, so that's a fairly straightforward one to start with. Let's think about the second step here. So chromate, I'm going to write that back up, plus 14 H pluses. I'm going to leave a little bit of space here just so that I can add if I need to. 2 chromium 3 plus on the right side, plus 7 water. So I'm just rewriting what we'd had before. Let's count up charges. So I have 14 pluses over here and 1 of the 2 minuses. So collectively, do this in green. Collectively, this whole side has a minus 12. 14 plus minus 2, yeah, that works. And on the right side, I've got collectively, the waters don't contribute anything. I just have 2 times 3, which is 6 plus. And so I'm oh, I'm sorry, this should be 12 plus on the side. So I've got a 6 plus on the right, and I've got a 12 plus on the left. That makes sense. So in order to get these to balance, then I'd need to add a total of 6 minus charges, or 6 electrons, to this left side. And now the overall, when I include this, becomes plus 6 as well. So these both half reactions have equivalent charges on both sides of the reaction. Okay, step 5 is we need both half reactions to have the same number of electrons being transferred. And this makes sense back to the sort of original qualifications of what a redox reaction is. Remember that if electrons are being pulled out of one species, those have to go to something else. So the number of electrons in the oxidation step have to be the same number in the reduction step. So let's go up and just poke around step 4 here. And what we see is in the oxidation step, we've got 2 electrons being transferred here in blue, and then in the reduction step we've got 6. That can't be true. The same number of electrons have to be transferred in both, which means that we just need to multiply one of the half reactions by some multiple. Sometimes you'd have to multiply both to get a common multiple. In this case, it's pretty straightforward. We can multiply just this top reaction by a factor of 3 to get this to be 6 electrons, and we'll have 6 electrons transferred in both. So I'm going to rewrite this then. This will be 6 chloride and 3 Cl2 plus 6 electrons, and then the bottom reaction will remain the same. So chromate ion plus 14 H plus 6 electrons makes 2 chromium 3 plus ions plus 7 H2O. I should say that I'm leaving out the state symbols in all of these right now just so that I don't have to write a bunch, but for good measure we should include those when we can. Okay, so the final, or pretty much final step before we do a check is just to add these two half reactions together. And when doing so, if we've done our due diligence, the number of electrons should cancel in both cases. And so, and that should make sense here because we've got 6 electrons in this first half reaction on the right side, and then we have the same 6 electrons on the left side below. So we can add these things up, and let's write this out. So get my black pen here. So if I write this whole thing out, add these together, I'm going to have chromate plus 14 of these H pluses plus 6 of the chlorides. That's going to yield 3 of these chlorine gases plus 2 chromium 3 pluses plus 7 H2O molecules. The electrons would cancel because they're on both sides of the reaction. And this will be our sort of final balanced redox reaction, but we can do some checks to make sure that we did everything correctly. And the check is to make sure the charge is same or equal on both sides. If the charge is not the same on both sides, we did something wrong. So let's go through and add these things up. So we've got a minus 2 coming from here. We've got a plus 14 coming from here. We've got a minus 6 coming from here. That sets this whole side up to be plus 6, if I did my math right. Yep. We've got a 0 coming from there. We've got a plus 6 coming from there. And we've got 0 coming from there, which sets this whole side as a plus 6. These two are equal, and so this seems to be a viable, fully balanced chemical redox reaction. So 6 steps there. You want to make sure that you practice this a bunch. The half reactions can be performed in either acid or base, and the balancing requires either acid or base. In this class, especially because we're doing this in a truncated version online, we're only going to balance in acid. Base isn't that much harder, but it's just going to take another half hour of discussing, and it's really not that important for you. So we're going to leave it at that and practice as much as we can with just the